Okay, so this is problem 2.2 out of Griffith's Quantum Mechanics textbook. And the question says, show that E must exceed the minimum value of V of x for every normalizable solution to the time-dependent Schrodinger equation. What is the classical analog of the statement? So the hint is very helpful. It tells us to rewrite Schrodinger's equation in this way. Then it says if E is less than Vmin, then psi and its second derivative always has the same signs. Argue that such a function cannot be normalized. Okay, so hopefully this makes sense. If we take the case where E is less than Vmin, so E is always less than Vmin, that means that this term here is always going to be positive. And obviously 2m over h bar squared is always positive. So in that case, let's say psi is positive. Well, if you take two derivatives of a positive function, that's also going to be positive. On the other hand, if psi is negative, okay, you take a derivative of that function, well, then psi double star is going, or not double star, the second derivative of psi is also going to be negative. Okay? Because that negative can just be factored outside of your derivative, take two derivatives, and you get the same sign. So hopefully that part makes sense. That's the first part I wanted to emphasize. The second thing I want to do now is talk about what this means. So the second derivative tells us about the concavity of a function. So concavity we call this psi, maybe call this x. A function like this we say is concave up. And that tells us when the second derivative of psi is positive. Concave up kind of makes a smiley face. That's how I always remember it. And likewise, a function like this, kind of sad, we call concave down, which we get from our second derivative being, in this case, negative. Okay, so graphically, that's what the second derivative is talking about. Okay, so that's great. Why can such a function not exist, or at least not a normalizable function? Remember, this is our rule for normalization. This integral has to equal 1. What that tells us is that if we have a function that, let's look at concave up, for example. If this is just increasing, it's never going to terminate at positive or negative infinity. And similarly, our concave down function would do something similar, except it would just always go down. It's going to bend away from our axis, or x-axis. So that is a problem because we want a function that will eventually terminate at the plus and minus infinity. So we want something that might look like this. Like this would be a great normalizable function to work with. So what we showed is, in this case, where E is less than Vmin, we're going to have non-normalizable wave functions. In terms of the classical analog to this, I believe what they're talking about is in terms of the total energy. So if you think classically like a particle, kinetic energy plus potential energy is your total energy. Well, at the very least, even if you have no kinetic energy, E being less than the potential energy doesn't really make sense. At the very least, it can be equal to your potential energy. So we might write an inequality like this. E is going to be greater than or equal to the potential energy. And in such a case, then we are not going to have any sort of motion. Will be some sort of static particle. So that's what I think he was getting at with the classical analog. But really the important part of this question is to show why E has to be greater than Vmin. Because if it's less than Vmin, then you're going to have this situation with concavity, which will lead to a non-normalizable wave function. So hopefully that helps. And if it did, please give me a like and subscribe.